All right, so welcome everyone, and thank you for joining us. Today we have the pleasure to hear Beatrice Bonga, who will talk about BMS-like structures in cosmology. Please.
Thank you, Mark. For even pronouncing my last name correctly, that's really nice. So, of course, I'm very happy to be at this non-local quantum gravity seminar. Brilliant name, by the way. And today I'll talk about, indeed, BMS-like structures in cosmology. With the ultimate game, of course, to understand gravitational waves at a more foundational level in cosmology. But of course, one of the first steps is to understand symmetries. So essentially the overview of this talk is that I'm going to talk about asymptotic symmetries in cosmological spacetimes. But before I do that, I want to spend some words, and with some words I mean essentially half the talk, about asymptotically flat spacetimes. And I think this will help you connect the differences and appreciate them. So an invaluable tool, as you all know, right, in pretty much all of physics is perturbation theory. And also, of course, in GR, this is true. So what we typically, or in many cases do, is that we split the metric into some background metric with some small perturbation. And this can be, you know, the background metric can be the Minkowski spacetime, can be Kerr, can be your FLW, anything you like, essentially. Preferably something with lots of symmetries, so that the problem is not too intractable. But of course, as you also know, is that if you give me some arbitrary metric, there is no canonical split between what the background is and what the perturbation is, right? If I give you some, you know, output of some numerical code where people simulated merging neutron stars or whatnot, there's really no way to make this split. Or, I mean, there is a way to make a split, but there's no unique way, right? It's completely arbitrary. And that is a challenge for understanding gravitational waves, right? Because ideally, we want to think of gravitational waves as those small ripples or perturbations on top of some background. Of course, luckily for us, there is a way out, and that is to essentially run away as fast as you can, far away from all the messy physics, the strong gravity regime where, you know, maybe matter is flowing around, spacetime is highly curved, whatnot, and you just run away as far as you can, all the way to infinity, where things become simpler and calm and peaceful, and you, as a theoretical physicist, can do your experiments, so to say, or your calculations. Now, how to do that? Well, of course, there are different ways to run to infinity, and it's important to run in the right direction. So, of course, what you can do is you can keep your spatial position fixed and just send time to infinity. And you would end up at time-like infinity. The opposite way, you can keep your time fixed and send your radial coordinate to infinity, so you end up at space-like infinity. And the third way is the way to go if you want to study processes like radiation, and that is to go into the radiation zone. And you go there by keeping your light cone coordinate fixed and sending r to infinity. So in Minkowski spacetime, that will be the coordinate u, which is simply t minus r. You keep that fixed and send r to infinity to go to the radiation zone. And the way to, I know, this of course, you know, those infinities don't fit on the screen. So a trick to bring infinity to a finite distance was introduced by Penrose into GR, and that trick is known as a conformal completion. So the idea is quite simple, right? So we start with some arbitrary manifold with a metric on it. So say, take flat Minkowski spacetime. Then of course the points r equal to infinity are not part of your spacetime because that's where your metric diverges. But what you can do is you can rescale your metric by a factor omega squared, where this omega you can just think of as being 1 over r. So if you now, then you'll see that this combination is perfectly well defined and smooth, also at omega equals 0. And omega equals 0, of course, corresponds to r equals infinity, right? If omega is 1 over r, then that's the case. And now that is quite nice, because now at omega to 0, nothing special happens, right? This new metric is completely smooth and regular, so you can attach all those points that were not part of your original spacetime to your new spacetime. So you can formally complete your spacetime, and that allows you to also draw conformal diagrams, right? Where now the infinities truly do fit on my page. And here I have my time-like infinity, my space-like infinity, and this radiation zone in which we're interested. And this radiation zone also goes by the name of scry. Now, of course, we're not just interested in Minkowski spacetime. Minkowski, I mean, it's quite boring, right? We're interested in this more general class, anything that's asymptotically flat. And that is defined in the following way, which is based on that trick. So let me take you through the definition. So the definition, right, essentially says, right, if you have a physical spacetime, you can conformally complete it, right, with m and g, where this g is exactly that omega squared times g hat like you saw, and such that your boundary, which is this scry, the boundary, has to have topology r cross S2. My omega and my new metric, my conformally completed metric, have to be smooth. Omega has to be 0 on this boundary, which I denote by this hat on top of the equality sign. And the gradient of omega, which of course is the normal vector to this surface, can be nowhere vanishing on scry. Now that last condition, it sounds maybe a bit weird, but that essentially ensures that omega is a good coordinate. Just like r, right, was a good coordinate, except of course on the boundary. But the nice thing about omega, that it is a good coordinate on the boundary as well. Now, up until this point, right, point 1 is essentially just pure math. There's no physics involved. It's just differential geometry. The physics comes in the second part of the definition. And that is, of course, that right, we're not just interested in any manifold. We want to describe solutions within GR. So, of course, we need that Einstein's equations are satisfied. But we don't want all solutions to GR. We want to indeed to model, right, these things that become asymptotically flat. So as you can imagine, right, that means that your matter field should decay and at an appropriate rate as you approach scry. And it turns out that, well, the right factor to choose here is omega to the power -2. T hat AB has to have a smooth limit to scry. So this really ensures that your spacetime is asymptotically flat. Now this definition is quite minimal, right? I'm always surprised how minimalistic it is, but it buys you a tremendous amount. So for instance, if you just look at Einstein's equations, you find almost directly that as a consequence of these quite minimal assumptions, that normal vector to scry is null. And that's also the reason why, of course, this surface is at 45 degrees, because indeed this is a null surface. And then closely related to that, of course, is that the induced metric on scry is degenerate, right? So it will be 0 plus plus. And that, of course, has to do with the fact that this is a null surface. Now you may say, okay, Beatrice, that's all very nice, but that factor of omega, how do you choose it, right? I mean, if omega is 0 on scry, then 3 times omega is also 0, right? So, I mean, isn't there a lot of freedom? And the answer is yes, there is a lot of freedom. In fact, there's almost, there's this functional freedom. So if I choose omega and you say, okay, well, I don't like that choice, I want to choose omega prime, you can essentially just rescale it by any smooth function that doesn't diverge or is 0 at the boundary. And that is a totally fine choice too. Of course, as a result, your conformally completed metric will be slightly different, right? It will be different with this little omega squared factor. And your normal vector will also be different with this omega inverse factor, where that omega inverse factor comes, of course, from the fact that the normal is just defined with the index up, right? Is defined with the conformally completed metric and the gradient of omega. So now if you prime everything, you now get the prime here. And of course, because it's the inverse metric, we get omega to the power -2 instead of 2. And these terms cancel out. And we get a factor of omega to the power -1 NA on scry. So this, why do I stand still at this point, right? Because this NA, this normal vector, and my Q are kind of the stars of today's talk, right? Because they form a universal structure that is essentially common, or not essentially, that is just common to all asymptotically flat spacetimes, right? And as you've seen, there is some conformal freedom in them. So if you have a Q and an N and you choose another one, as long as they're conformally as long as they're equivalent with these particular omega factors, then they form this universal structure. So this tells us essentially that any, absolutely any member of this class of asymptotically flat spacetimes will have the same Q and N as that of Minkowski spacetime, right? So whether you have Kerr or something else, they all will have the same structure for Q and N as flat spacetime. Now you may wonder, okay, but we know that there should certainly be something different, right? Because if everything gives us the same answer, it's not so interesting. And of course, something will be different. And in particular, gravitational radiation really distinguishes between different members of this large class of spacetimes. But that is encoded in the next order structure. And it's not encoded in this universal structure. So it's not encoded in the Q and N. Now the universal, so before I move on, so let me say some key points again. Right? Nowhere in this construction did we introduce some split of background and gravitational waves. This happened naturally at infinity, right? Where the universal structure is like, your background metric. And the first order structure, which I didn't show to you, but I mean it's there, is that what contains the gravitational radiation. And it's completely fully non-linear. So this is really proper non-linear GR and allows us to still make this canonical split. And I think this is a moment where to say, wow, this is absolutely so beautiful. Yeah, really. It makes me really happy that this kind of structure does exist in GR. Now, to give you a little bit maybe of a more concrete idea, let me take you just through this very simple example of an asymptotically flat spacetime, which is of course flat spacetime itself. Right? So we start with the physical metric in our usual TR theta phi coordinates. We first perform coordinate transformation to UR theta phi coordinates because we keep in the back of the mind, right, that we want to take the limit to null infinity. So it's a useful thing to work with null coordinates. Okay. And then we notice actually that this r squared, right, we see that if we take r to infinity, this part diverges, which is immediately obvious. Right? But in fact, this dr also diverges. And you can see that, right, if we choose omega to be 1 over r, then if we take the differential, so dr, it will be minus omega to the power -2 d omega. So as we send r to infinity, or in other words, omega to 0, we see that this differential dr also diverges as omega to the power -2. So in a way, you could say that dr also diverges as r squared in the limit to infinity. So what we then do is say, okay, well, that's not so great, but because we are interested in going to infinity, so we do that trick of the conformal completion. We multiply this metric by omega squared, and here we get the omega squared. Here the omega squared cancels with the omega to the power -2, and the omega squared cancels with the r squared, and we end up with this metric, which then, of course, on scry, right, where omega is 0, is just simply this. And this is the induced metric, and in fact, right, this induced metric is exactly the part of the universal structure. And any other example of an asymptotically flat spacetime, such as the Kerr-Newman spacetimes or Weyl space, or certain subclasses of the Weyl spacetimes, etc., will have a similar induced metric. Now, of course, flat spacetime itself is a little bit boring, right? But in fact, right, in any generic asymptotically flat spacetime, you can introduce a coordinate system in the following way. So this is, the top part is completely generic, but the fact that we say this is an asymptotically flat spacetime is encoded in the fact that I demand that these coefficients, u, v, the gamma, the w, have to satisfy a particular decay. So I'm saying that, you know, as I approach scry, u needs to decay as 1 plus some function b, which is a function of the coordinate u and these coordinates on the two-sphere over r squared plus extra terms. Now, to give a little bit more structure, because this seems a little bit maybe overwhelming, let's color the important terms. Right? So we see that indeed, as we send r to infinity, all these other terms drop out, and I'm left with the Minkowski spacetime. So that's the yellow part. The mass of the spacetime, so, you know, say you want to describe something like Schwarzschild or something more general, right, is encoded in this function, which is called the mass aspect, because, well, in Schwarzschild is a constant, of course, but generically it's a function of u, theta, and phi. This b encodes the angular momentum aspect, which plays a similar role to the mass aspect, but instead of, you know, encoding information about the mass, this part of the metric encodes information about angular momentum. And this part of the metric, this 1 over r part on the two-sphere part, encodes information about the radiative degrees of freedom. Now you may wonder, okay, well, but I saw just 2 different definitions of asymptotically flat spacetimes, and in fact, they're completely equivalent, right? So the geometric description out of Penrose with the conformal completion technique, right, that just had, you know, those 2 conditions, it's completely equivalent, and in fact can be your starting point to derive this metric with this particular falloff. So you can either say that, okay, if you have a particular metric and you can put it in a coordinate system such that your metric satisfies this decay, then you know that is an asymptotically flat spacetime, or you can check the conditions in the geometric description. They're really interchangeable. So as a result, we can also describe the asymptotic symmetry algebra in 2 equivalent ways. So the asymptotic symmetry algebra is the algebra of all space-time diffeomorphisms that leave the universal structure at scry invariant. Now, in terms of the universal structure, that means that, well, it's essentially all vector fields that map Q to another member in the conformal class, right? So for that reason, you see here that you get back Q with some conformal factor. And similarly for N, you get N back with some conformal factor here. So that's one way of thinking about the asymptotic symmetry algebra. But it may be, in coordinates, it almost looks more intuitive, right? So if you drop the hat here and the omega squared, this would just be the condition for a killing vector field in your spacetime. But of course, right, most spacetimes don't have killing vector fields. And in a generic spacetime, there are no symmetries. But for this large class of spacetimes, there are these things that are asymptotic symmetries. And the asymptotic is reflected in the fact that this equality only needs to be satisfied at scry, and that you have this vector of omega squared here. Now, what is the asymptotic symmetry algebra for an asymptotically flat spacetime? Well, that turns out to be the Bondi-Metzner-Sachs algebra, so also known as BMS for short. And this algebra is bigger than the Poincare algebra, right, which is the algebra of translations and rotations, including, of course, the boosts. But the BMS algebra is the combination of supertranslations and rotations. So what are those supertranslations? I know many of you are expert on that, but for those that are not, supertranslations you can essentially think of as angle-dependent translations. So if this were a translation, this would be specifically a linear combination of your spherical harmonics, right? So if you were to, and of the spherical harmonics with L equals 0 and 1. So if you were to decompose this in spherical harmonics, it's really only that subset. Whereas for supertranslations, this can be an arbitrary function of theta and phi. And of course, our rotations are encoded in here, and they need to satisfy this conformal killing equation on the two-sphere. Now, I think at this point is a very good question to ask, okay, what is this actually good for? Like, what would we do with this whole BMS algebra? And my take on it is that BMS quantities or BMS vector fields, they provide quantities with a physical interpretation. So in particular, right, the BMS algebra is this bigger algebra, but it does have a translation subgroup. And that translation subgroup you can use to define things like mass and linear momentum, which really are non-trivial concepts, right, in general relativity. Similarly, there are rotation subgroups, in fact, actually many, but I'll not go into that detail, that allow you to define angular momentum up to the supertranslations, which are connected to the fact that there are many, but again, minor detail. And then, of course, there are the supertranslations, and those are intimately connected to, say, the gravitational wave memory effect. Now, in all of this story, right, there was a critical assumption, and that was that as you move far away from sources, your space-time becomes flat. And it bought you a lot, right? We got these nice Bondi sex coordinates, we got the Bondi Muse tensor, we have the BMS symmetry algebra, these nice 1/r expansions, scaling theories, whatnot. It's fabulous, so to say. Lots of tools, lots of ways to understand your physical system. But of course, as we know, expanding spacetimes are not asymptotically flat, right? For the very simple reason that these spacetimes are homogeneous, right? So the curvature is the same on any given time slice, and there's really no decay in any direction. So then the very valid question is actually, so why do we actually assume asymptotic flatness if clearly our own universe is not asymptotically flat? And that was actually a question that was already asked by Weber, I believe, at a conference in Warsaw in 1963. And I looked at the conference proceedings and found this nice answer by Berkman, who said the following: the only answer I could give is that the investigations date back less than 2 years, I believe, and people have just simply started with the mathematically simplest situation, or what they hoped was the simplest situation. To which Bondi added, indeed, I regret it as much as you do that we haven't gotten yet to the point of doing the Friedman universe. And that's more or less where you know, things left off and stayed until the 60s and hadn't really drastically been changed. Now, so that's exactly what we set out to do. We decided to look at these expanding spacetimes and try to understand gravitational waves and symmetries in this larger class of spacetimes, in particular in cosmology. Now, in order to do that, it's important to make a distinction between two different types of solutions. Right? So if we describe expanding spacetimes, they're the ones that expand faster and faster, the accelerated ones, right? Such as our current universe is at the moment. And for example, right, if you have a de Sitter universe, this will have an expansion that's going faster and faster. But there's another large class of solutions that are decelerating. So if you have, for example, a matter-dominated universe, right, which happened in our past, or radiation-dominated universe, those spacetimes have a scale factor that does expand, but the expansion slows down. So what we're going to look at today is the case with no cosmological constant and the case for which the universe is decelerating, such that in that case, actually, the radiation zone, right, our sky, is still a null surface. So I'm leaving aside the case with a cosmological constant where the radiation zone really drastically changes and becomes space-like. So we're focusing on this. And just as asymptotically flat spacetimes, right, are modeled after flat spacetime itself, what I'll do is, here is the same. So I'm going to model this large class of spacetime that I'm interested in, but I'm going to first study this archetypical canonical example, which will be decelerating spatially flat FLRW spacetimes, right? Which, as you can know, or as you know, you can write as the flat metric times a scale factor squared, where this scale factor, in terms of conformal time, is given by eta to some power. And this power I've written in this somewhat maybe strange looking way with S, where this S is directly related to your equation of state parameter, W. And for those, as a reminder, the equation of state parameter is that number that relates the pressure and the energy density of your perfect fluid. So to get a little bit of a feel for that, W equals 1 describes a stiff fluid, 1/3 describes radiation, W equals 0 is dust, and W equals -1 can model or mimic the behavior of a cosmological constant. Now, decelerating FLRW spacetimes have W larger than -1/3. And this range is somewhat strange and awkward, and that's why we introduced S, because these limits on W nicely translate into these simple limits on S. So S has to be between 0 and 1. In fact, actually, it has to be strictly larger than 0, but we've included the case with 0, because as you can see, right, the case with 0, S equals 0, your scale factor would just be 1. And that is just flat spacetime. So this allows you to take the limit to flat spacetime. So if you're confused about what's going to come next, and you want to do a check in the back of your mind, just send S to 0 and you get back to the flat case. Now, these decelerating FLRW spacetimes, we can also look at what their conformal diagram is. And I think there are sort of two ways to arrive at the same conclusion. The simple way is to say, hey, this is my flat metric, but of course I know that eta is doesn't run from -infinity to +infinity as it does for flat spacetime, but runs from 0 to infinity. So the conformal diagram for this spacetime should essentially be exactly the same as Minkowski spacetime, but just cut in half, right? Another way, a more brute force way, is to just do a bunch of coordinate transformations. Very similar to those what you would do in flat spacetime, right? So you introduce some new coordinates, in particular u and v, which are these compactified, right? They range from -pi to pi, and v, well, is always larger than the absolute value of u to pi. And these are now compactified, and in these new compactified null coordinates, we can choose a conformal factor, in particular this conformal factor, such that the conformally completed metric is just simply this new, very simple looking metric. And in particular, note, right, there's an important point here, the point where u equals v and where v equals pi are not included, right? They're not part of the original spacetime. But if you look at the behavior of this metric, you can see that the metric is perfectly smooth everywhere, including the points where v equals plus or minus u and v equals pi. So we can attach those points. And indeed, when we do that, we get this conformal diagram that I already told you about. So this is the conformal diagram of an FLRW spacetime, of a decelerating FLRW spacetime. Of course, in the past, here is where our Big Bang is. We have spatial infinity. time like infinity, and scry, which is described by the surface where v equals exactly pi. Now, and if we look at the behavior of this conformal factor of omega, it's of course chosen in such a way that omega is nicely zero on all scry. Of course, there's a side note, omega diverges at the Big Bang, but that's totally fine because we're not interested in that part of spacetime anyhow. We are really interested in scry. So since it's nice and regular there, it seems like we're in business. Except that near scry, if we actually look at the coordinates specifically, we see that omega scales in this particular way, and the gradient of omega scales like this. Now, this may not worry you, but remember, there were two conditions in the asymptotically flat case that we imposed. And in particular, right, we imposed that omega had to be smooth on scry, and that the gradient had to be nowhere zero on scry. Exactly these conditions are violated, right? So this is not smooth, right? Unless s equals to 0, of course, but anywhere in this range from 0 to 1, this is not 0 because of this fractional power. And this thing is in fact actually everywhere 0, of course, unless s equals 0, but that was the asymptotically flat case anyhow, but exactly because of this overall factor. So this seems worrisome. But then you may say, okay, but Beatrice, you told us, right, at the beginning that there was a lot of conformal freedom in choosing that omega. So weren't you just being stupid and you just chose the wrong omega? Look, if you choose this particular choice of omega, right, where I'm rescaling your omega with this little omega, then everything is fine. Omega is nicely smooth and your gradient is nowhere 0. So why are you making such a fuss about this? Well, the answer to that is, of course, well, you are, of course, perfectly allowed to do that. But if you do that, that also means that you need to rescale your metric. And when you look at your new metric, this, of course, now diverges, even at scry. Right? The whole point of doing this business of conformal completion is such that, you know, everything is nice and smooth at scry, or at least, you know, n times differentiable, where n is, well, can be relaxed somewhat, right? But let's, you know, think of just the smooth case. And that was, you know, the whole goal. So this completely defeats that purpose, right? Now you can no longer use all the nice tools of differential geometry. So it seems a little bit like you're at an impasse, like what to do now? To that, actually, there is a remarkably simple solution. So if we look at omega, we saw that it has all these problems, but omega, well, omega is not smooth. Omega to the power 1 minus s is in fact smooth, right? We look omega to the power minus 1 minus s, this factor now does become smooth. And in fact, of course, right, if omega is 0 in scry, omega to the power 1 minus s is also 0. And it also nicely resolves this issue of being the fact that the gradient is 0 everywhere. So now if you look at the gradient of this factor, it is indeed non-zero on all scry. So the idea is to still use the same conformal factor, same omega, to find a conformally completed metric, but to define the normal to scry using omega to the power 1 minus s instead of omega. So, and in fact, we added this factor of 1 over 1 minus s just so that there would be less factors of s floating around. But this is, of course, not key. Right? So the key point is that we used a different way to define the normal factor. And this normal factor is, you know, perfectly regular and has all the right properties.
Beatrice, can I ask a question? So
yes.
You still complete your space-time using omega square?
Yeah, correct. Correct.
Okay.
So we still use omega square to complete the spacetime, but we define a different, or use a different way to define the normal.
So these spacetimes are not asymptotically flat in the usual sense.
No, they're absolutely not. No, that's true.
But they are in this generalized sense that
they are in this, yeah. So we've given them a different name. So we will call them cosmological spacetimes, or spacetimes with a cosmological null asymptote, to highlight the fact that they are not asymptotically flat, but yeah, more general. In fact, actually, so this doesn't quite fix the problem, or all the problems, right? So for this reason, this is one of the reasons why FLRW spacetimes are not asymptotically flat. But there's another reason.
Can I ask you a question? I mean, if you have matter which is given by dynamical field, then the equation of state S is not a constant, right?
That's correct. Yes.
So does that mean that you have to impose it, that it becomes a constant or something?
Actually, yeah. So we indeed, in the way we're describing this, it has to become a constant near scry.
Is that a restriction? I mean, in terms of, I don't know, usual radiation or?
So I don't think it is a restriction, but well, of course, it is some restriction on the class of spacetimes you are allowing. But so I don't think it is a severe restriction on the ultimate goal that you want to do if you want to study radiation. But actually, I will come to that. I think I'll return to your question. Is that okay?
Yeah.
I'll return to it at a later stage, because this is a key question, to which I do not fully have the answer yet. But so in addition to this difference, right, this is one of the reasons why these spacetimes are not asymptotically flat. But there's of course another, I mean, almost more in your face difference, and that is of course the presence of matter. Right. For the asymptotically flat case, right, we demanded that the stress energy tensor should like nicely decay. But for FLRW spacetimes, right, they're homogeneous, so matter is everywhere. There's no decay. And in fact, right, if you calculate, for example, what the traces of the stress energy tensor using those conformally compactified coordinates, you indeed see that this is non-vanishing, it's non-zero. But in fact, things are worse, right? So it doesn't just not decay and the trace is just not non-vanishing, but if you probe specific components of the stress energy tensor, you find that for these decelerating FLRW spacetimes, that there are diverging parts. And in particular, right, if you want to think again of omega being like 1 over r, this is diverging as r squared, right? And this is a term that diverges as r. And then there's some finite piece. So really,
just a clarification here, TAB is in the physical spacetime or the compactified spacetime?
Physical spacetime. Yeah. So this is the matter of the physical spacetime, but it badly diverges. Now, interestingly enough, this part is universal in the sense that, what I mean by that, right? If I choose some omega and you choose omega prime, we will find exactly the same factor here. This part, the subleading part, it does depend on your choice of omega. There's no, right, does depend on your choice of conformal factor. And for instance, for some particular choice, you can calculate what it is, and this is the expression. So the matter parts are diverging, and then they're finite pieces. Quite different from, right, what happens in the asymptotically flat case, where omega starts to, or this t hat AB starts to be non-zero only at, not at within this finite part, so at order omega, so much higher order. So as I said, right, the asymptotically flat spacetimes are all modeled after flat spacetime itself. So similarly, we are going to define this class of spacetimes with a cosmological null asymptote modeled after the case of these decelerating FLRW spacetimes. Now the definition is almost similar as to the asymptotically flat case, but of course two important differences, right? The fact that we define the normal with this omega to the power minus s factor, right? So, and in particular, right, related to that, we don't demand that omega is smooth, but that omega to the power 1 minus s is smooth. And then, of course, Einstein's equations need to be satisfied, but such that the trace exists for the stress energy tensor, and that, well, this is just the same as I said essentially on the last slide, right? So that there is this badly diverging part and this sub-leading diverging part to the t hat AB. Now, given this structure, right, we can play the same game and ask ourselves the question, okay, what is the universal structure? And it turns out to be very, very similar, right? So the universal structure will be Q and N, but of course now the Q's and N's are not just related by this omega squared factor. Well, that's of course the same, but here the N's are related not with omega to the power minus 1, but with omega to the power minus 1 minus s, which comes from the fact, right, that the definition of the normal has this minus s in here. And then we can ask ourselves the question again, what are, what is the asymptotic symmetry algebra? Or in other words, right, what are all the vector fields that map me from one Q and N to another member in this family? And it turns out, right, since this structure, right, the universal structure in the end is really very similar, except for that minus s, you can imagine that if you do the analysis, right, that you do indeed find that the asymptotic symmetry algebra is indeed very similar to the BMS one in the asymptotically flat case. So we do find that it is the Lorentz algebra, the semi-direct product with supertranslations. But in this case, the supertranslations are S-dependent. So you may say, okay, wow, but I mean, didn't we know this already? Wasn't there that paper, from 2016 that wrote nicely BMS in cosmology? And it's true that this paper exists, but it's essentially wrong because they say that it's exactly BMS in cosmology. But that's not quite right? There's a twist. As you know, right, in the supertranslations, right, I told you it can be some arbitrary function on the two-sphere times the normal vector. And now this arbitrary function on the two-sphere has a conformal weight of 1 plus s instead of just 1, which is the case for the asymptotically flat context. And you can see that scaling in this particular way. Sorry, I will not go over the details, but the point is that, right, if you choose to write the same supertranslation in a different conformal frame, then your f will be related to, say, my f through this particular way, through the omega factor of 1 plus s. And you say, okay, what? Who cares about, the conformal weight? That's just, mathematical blah, blah. But in fact, actually, this has a really drastic consequence. Because as a result, there is no translation subgroup. Right? So we do know that in the BMS context, even though we do have this infinite dimensional algebra of these super translations, there is a finite dimensional, in fact, parameterized by 4 parameters, finite dimensional subalgebra, which are exactly your translations. But the fact that this function f now has a conformal weight of 1 plus s shows us that there's no such translation subalgebra. In fact, there is no finite dimensional algebra of the super translations. You're just stuck with all super translations. So you may wonder, okay, wait, but how about FLRW spacetimes themselves? Isn't that, what you're saying, isn't that in contradiction with these FLRW spacetimes that clearly have translational killing vector fields? So shouldn't they, become part of the asymptotic symmetry algebra? To that, the answer is actually no, because this is actually very similar to the absence of a unique rotation subgroup for asymptotically flat spacetimes. Right? We know that in asymptotically flat spacetimes, there's called this super translation ambiguity for angular momentum, which has to do with the fact that there's no unique rotation subalgebra. But we know examples, right? Schwarzschild, there's clearly a unique rotation subalgebra. So the fact that particular members of the class have extra structure, right, extra symmetries, doesn't mean, right, that all members of the class need to have it. So similarly here, what we find is that even though, right, everything is modeled after these decelerating FLRW spacetimes that do have a translation subalgebra, the general class does not. So as a result, right, we wrote a paper with a very similar title referring to the original work, just to say that actually, well, it's not BMS, but they're BMS-like symmetries in cosmology. Right? A fairly similar structure, also the Lorentz algebra and supertranslations, but just not quite the same. And in particular, the fact that right, there are no there's no subalgebra of translations means that, for example, the notion of mass and linear momentum within this larger class of spacetimes, it's not clear at all what that should be.
So Beatrice?
Yeah.
Maybe you're going to explain this, but is there a simple reason why this was missed in the previous paper? Was there one clear mistake that was made?
As a pure mistake. They missed, for instance, they did a more, in that original paper, they did a more coordinate-based approach. And they just failed to notice, for example, that the gradient of omega is 0 everywhere and things like that. So there's several mistakes like that.
Okay.
Yeah. Also, they focused on, interesting enough, when they studied the algebra, they focused on, which is strange, but they focused on by factoring out the a squared and then studied the algebra of the, well, the metric minus the a squared, but that I have no deep understanding why you would do that, because that is simply wrong. But I think, you know, what we did in this paper is both the geometric approach and the coordinate-based approach, and it's really a unique unifying picture. And I think if they had done that, they probably would have noticed their mistake as well. So as I said, right, yeah, we also did a coordinate definition. So if you, I don't know, like the coordinate definition better, you could introduce coordinates. So if you do that for the conformally completed spacetime, right, then where now, of course, omega is not a coordinate, but omega tilde, which is just omega to the power 1 minus s, just a shorthand for that, right? Because we know that this is smooth and your coordinates should be smooth. So if you do that, then using the geometric definition and Einstein's equations, you find a particular fall-off in this way. Now, this may not be super informative to you, but let me contrast this with the asymptotically flat case, because I think it's nice to see the difference. Right? So in the limit to the flat case, you notice that this W2, which in principle for us is an arbitrary function of u and the coordinates on the 2-sphere, is just simply 1. In the flat case, this W3 is minus 2 times the mass aspect. Of course, these two terms are all 0, right? Because they are those taus, which refer to the matter terms. Here is what in the asymptotically flat context we would call the angular momentum aspect. And this C in the flat context again is what encodes your radiative information. Now, of course, that intuition from the flat context, you should be very careful to carry that over to in this setting, right? We have not shown, for instance, that this W3 is really what ends up being playing the key role in what is mass, because we actually don't have a good definition of what is mass in this larger class of spacetimes. So you should be a little bit careful of carrying this over, but I hope that that will give you a little bit more intuition as to what these terms possibly might physically mean. Now, the interesting thing of these coordinates is, well, maybe not directly the relation with this, but it allows you to do this nice computation of the Newman-Penrose scalars. And in particular, if you focus on these, psi4, psi3, and psi2, and you calculate what they are, you find, well, something like this. And the key point is that the fact that these two terms, that psi3 and psi2, are non-zero on scrying, means that there's no peeling. And in the flat case, of course, there is peeling, because in the flat case, S is 0, so this term is indeed 0. And S is 0, so all these terms vanish. And W2, as I told you, right, W2 is exactly equal to 1. So this one cancels with that one, and this is indeed 0. And this is not the case. And here it's not the case, right, because we have all these tau terms appearing. And these tau terms are exactly those matter terms. So in this class of spacetime, in this cosmological context, there's no such thing as peeling, which a priori is I mean, that's just what it is. But, and it's nothing, I mean, to hold against the theory. But it makes, again, studying gravitational waves and disentangling what is radiation and what is not a little bit more complicated, because a lot of our intuition is based on these peeling properties. Now, coming back to the question of Laurent, and I think it's related to this one, do you have any other explicit examples of spacetimes that fall within the class that you described, right? You had this nice model of decelerating FLRW ones, but are there any others? And to that, the question is, well, unfortunately, I don't have any concrete analytic, known examples. So I cannot say, oh yeah, there's something like Kerr in this context or anything like that. But what we did do is we were able to show by construction that the class of spacetimes that we're describing is at least as big as the asymptotically flat context, right? So as the asymptotically flat spacetimes. Now, unfortunately, in this proof, what it did not allow us to do is show whether those spacetimes, are physically interesting. Right? Ultimately, what you're interested in is, of course, and that's the reason, of course, why asymptotically flat spacetimes are so common and often used, is that they really model physical systems. And this construction, unfortunately, did not allow us to do that, nor were we able to actually show that our definition is stable under linearization. In fact, actually, in the asymptotically flat context, that's also a tricky proof, which was done by Xantopoulos and Garrosh with some, magical gauge choices and such. And this, as you can imagine, the presence of those matter terms really makes this even more complicated. So these two things are still open, and I think the biggest caveats in this whole enterprise that we did. Nonetheless, I think this is a really nice geometric construction to study spacetimes beyond the asymptotically flat context and study, in particular, those in cosmology. So what we found is that the asymptotic symmetry algebra is BMS-like. So not exactly BMS, right? It's not isomorphic to it, but it does share the structure that it is the Lorentz algebra with supertranslations, but it doesn't have this translation subalgebra. So in particular, right, these notions of mass and linear momentum, what they should be in this context is not so obvious. So for future applications, well, I hope, well, to address the biggest caveat, right, that there are, that we can show that there are indeed many physically interesting spacetimes that fall within this class of spacetimes. And if they do, then we should really look at the next order structure. And so in this paper, we really only looked at the universal structure, but in the next order structure is where the gravitational radiation is hiding. So that would allow you to study rigorously gravitational radiation produced by compact sources in cosmological spacetimes. It would allow you to study gravitational memory effect, charges and fluxes, a link with future null infinity with future time-like infinity, and anything essentially that is your favorite topic within asymptotically flat spacetimes in principle should carry over to this context. So thank you for listening, and I welcome any other questions.
Thanks, Beatrice.
I have a few questions, if nobody else.
I think you're
Yeah, please.
free to.
One technical question. Do you have a slide where you can show us how the supertranslation acts on the shear?
Do I have that here? Let me see. I have some backup slides, but let me.
Just to see a more technical way why.
I know what you're asking. I know we have it in the paper, but I don't have it in the backup slides. Sorry.
Okay.
But it is in the paper.
Okay, I'll look at it. Okay, no, that's very, very, very nice. In fact, I was wondering how, somehow we could, it's a very natural question to be able to include this question of asymptotic symmetry and charges and all we know to more general space-time. So that's very nice. One thing though is, okay, because you don't have the peeling theorem, I think it's going to be a bit of a challenge. I don't think it's going to be impossible. It's going to be a bit of a challenge to have a canonical representation of this symmetry algebra, because you have you have more I don't know, more divergent boundary conditions, and usually it means the symplectic flux diverge and etc. etc. So far they are not yet realized canonically on a phase space, right?
No, that's true. We haven't done that type of analysis. We really focused on, right, indeed, you're totally right. So there are multiple ways to study the asymptotic symmetries. I presented two, but mostly focusing on the universal structure, but you can also indeed study them through the symplectic structure. And indeed, we haven't done that because, like what you said, well, we didn't have the guts to do it, essentially, but it will be more difficult.
Well, we can chat about that. We're developing techniques to do asymptotic renormalization, which are very powerful now. So.
Oh, fantastic! Yeah, no, we should chat.
Yeah, and in fact, it's tied up to my second question, because you mentioned this notion of universal structure, but in the study of asymptotically flat, we also know now that we can relax that. There's other type of geometrical structure which are like Carolean structure, which are deeper than this.
Yeah, actually, this. Well, I didn't mention the word, but this is also a Carolean structure.
Yeah, but if you use this more general asymptotic structure, then we know that the symmetry group is not just BMS. BMS is just a subgroup of the asymptotic symmetry group.
Yeah, so right? So I know of some ways to generalize it, and I also know that I may not be aware of all the possible ways to generalize BMS, but I know that in some ways of generalizing BMS, you can also show that there's no translation subalgebra. And for that reason, we really restricted to this context, because I think it's important to highlight that difference, right? Because otherwise, it doesn't seem like a difference, but I think this is truly a difference between the cases.
Yeah, no, if you restrict to BMS, it's true that once you're fully extended, there's no translation algebra anyhow, right? Because you have the structure of the vacua is much more general.
Yeah, so it's more general indeed. So I think there's somehow a balancing act between, well, how general do you want to be and how much structure would you like, right? I don't think there is a wrong answer, right? It's just almost, yeah.
In fact, I'm still
no, from the classical perspective, it's complicated. I mean, anytime you restrict your boundary condition at infinity, you're in fact restricting your initial condition. So at some point, the BMS-like conditions are forbidding certain black hole merger that happen in space-time. So at some point, you have to relax them. From the point of view of quantum gravity, of course, you want the biggest symmetry algebra. Because at the quantum level, there's no, you want the entire phase space. But
yeah, correct.
Still an art, of course. Still an art. That's very nice.